Let's write the Lewis structure for phosphorus pentafluoride. And if we look at the periodic table, we'll see that phosphorus is bringing 5 valence electrons to the total. Each of the fluorine is 7, and there are 5. So 5 sevens are 35, plus 5 more is 40. So the total valence electrons for this guy here is 40. And that's what we have to arrange around these atoms to draw the best Lewis structure. Phosphorus is in the center, and I will arrange, excuse me, my 5 phosphorus. And just to reiterate, the Lewis structure is not indicating anything about the bond angle or geometry or shape, only the bond pairs and the lone pairs. Let's make single bonds between all of the atoms that are bonded together. 2, 4, 6, 8, 10, and I'm going to go up to 40. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. So I've used up all of the electrons. I have an octet of electrons around each fluorine. That's great. But one thing that I had to do was put 2, 4, 6, 8, 10 electrons around phosphorus. Is that possible? Let's bring back the periodic table for a moment. This is an exception, clearly, to the octet rule, and it's labeled as an expanded octet. So here's phosphorus. Phosphorus has atomic number 15. For any central atom that has an atomic number 15 or greater, so for phosphorus or larger, because we see this with sulfur as well, that central atom in a molecule is able to accept more than an octet of electrons. It can take 10, and it can also take 12. We won't put 11 because we know that bonds are in pairs. So we have phosphorus, atomic number 15, or elements larger that our central atom can be an exception to the octet rule in a Lewis structure drawing or approach, and it can have 8 electrons or 10 or 12. In this case, it has 10. So this is an exception, and it's called expanded octet, exactly. And that's exactly what it is. We say, especially in older books, that those electrons are kind of back bonded. And what do we mean by that? Is that if we look at phosphorus again, we know that it's in the third row of the periodic table. And in the third row, we're filling the 3s electron orbitals, and then there are no d's, and then we get to the 3p. But we do know that the d orbitals that exist, excuse me, I'll say that again. We do know that the d orbitals exist on the third level, but we know that they're vacant till we get to the fourth, and that's when they're filled. So there's argument that there's room in the atomic orbitals for these electrons, and we don't have to get into that level of detail. And again, this is a model, and it kind of breaks down. But PF5, this is the Lewis structure. It is an exception. Comes under the category of expanded octet exceptions because there's more than 8 electrons around the central atom. Don't put more than 8 electrons around an outer atom. It's just got to be central or a local center in a larger molecule. Excuse me. What is the formal charge on each fluorine? Formal charges. Well, each fluorine is equal to 7 minus 1 minus 6 equals 0. And the phosphorus, it has 5 valence, minus half of the bonding is 5, minus the total non-bonding, which is 0, and that's 0. And so everything is adding up to 0. This is a molecule that has no charge, and so that's great. We have one more exception to the rule. I told you there were 3 exceptions. One of them is the expanded octet, one we've seen already, and that was, well, less than 8 electrons around the central atom, the electron deficient species. And our third and last exception for writing Lewis structures is when we encounter a total odd number of electrons, because we can't possibly use up all the pairs. And so a good example of that is nitrogen monoxide, NO. This is a neutral species. It's a gas. And I have nitrogen brings 5 electrons and oxygen 6. So I have a total here of 11 valence electrons to place in this molecule as bonds and lone pairs. And whenever I have nitrogen and phosphorus, I often wonder if we're going to have an odd number total, because nitrogen and phosphorus each have 5 valence electrons, so they're bringing an odd number of electrons to the total. But oftentimes they're associated with a charged species, and so you're adjusting that by 1 plus or 1 minus sometimes. Anyway, we have 11 electrons here, and so what's the best Lewis structure that I could draw for this? I know I'm not going to be able to pair everything, but let's take a shot. 2 electrons here to indicate a single bond between the 2 atoms that I know are bonded to each other. And then I tried my best to do an octet of electrons around each of the outer, let's say, atoms. Kind of hard to tell which is central when I just have 2, but in any event. So I have 2. 4, 6, 8, 10, and then I have this 11. Well, 2, 4, 6, 8, lovely. 2, 4, 5. I can make this a little closer to 8. I know I can't make it 8, but if I take this pair and share it here as a double bond, then I have a double bond to oxygen. It leaves me 2 pairs here, 1, and then this, so it's a radical species. So I have 2, 4, 6, 7, 2, 4, 6, 8. That's all right. You might draw, and we're really not in a position to argue which is the better one with this in the scope of our first year course. You might draw, some of you, something like this and put the unpaired electron on the nitrogen, right? Because I could have done it the other way, and that would be 2, 4, 6, 8, and then 2, 4, 6, 7, but all in all keeping 11 electrons. So this one or this one. The question is, which is where are you most likely to localize that single electron, making it this a radical species. Oxygen is more electronegative, so some might argue this, and some might argue, well, nitrogen has the odd number, so stick it on the nitrogen. So we will accept either structure as your best Lewis structure for nitrogen monoxide or similar radical species. So just as the one above was in the exception category called expanded octet, and the one before that electron deficient species, this is paramagnetic. Because of course I don't have all my electrons paired even in the molecule. So this is a paramagnetic species or an odd numbered total valence. I'll encounter that. Let's do ozone as our third and final on this short video. And ozone is O3. So I have, we know it as a very reactive species, of course, and I have oxygens all bound to each other. So each oxygen has 6 valence, 3 6s are 18. So I have 18 valence electrons here to place. Oxygen, oxygen, oxygen. 2, 4, then to the outside, 6, 8, 10, 12, 14, 16, and then 18 I'll put on the center. So complete the octet on the outer ones, and if I still have electrons left like I did here, I'll move to the center. 2, 4, 6, 8, lovely. 2, 4, 6, 8, great. 2, 4, 6, I need a pair. So I could take it from this side, or I could take it from this side. So I'm going to have 2 resonance structures for ozone. And they are, when I have resonance, even if it's not a charged species, I use my square brackets. So this is oxygen. I'll put a double bond here and a single. So that was like that, that. And the other resonance structure. These are called resonance arrows. And the term as a phenomenon is resonance. And I have this. They don't really look like they're different structures because if you were on the other side you would see it as this, but we do draw them as two resonance structures. And the reason is because when I do, let's say I want to do an analysis of this molecule in the gas phase, I can determine experimentally that the two oxygen-oxygen bonds are chemically, physically the same. So neither a double or a single. You can imagine that a single bond is longer than a double, and a double is longer than a triple because it's that density change. So a triple bond is quite short actually, and I can do an experiment using a simple instrument to see the energies of these bonds and their bond lengths by how they interact with infrared light. And the experimental evidence tells us that these two bonds are the same. So there's somewhere in between a double and a single, in fact. So sometimes people will draw each with a single and then a dashed line underneath to indicate somewhere between a single and a double. But we are going to draw our resonance structures like this. And we can, let's write the formal charge. And let's do it in our head this time and just write it in. So oxygen, 6 minus 1, 2, 3, 4, 5, 6. Oxygen, 6 minus 1, 2, 3, 4, 5. 6 minus 1, 2, 3, 4, 5, 6, 7. So I see that the double bonded oxygen has a 0 formal charge. The single bond oxygen with 3 lone pairs has a -1 formal charge. And the oxygen in the middle that has a double and a single and 1 lone pair is a +1. So those are the formal charges on ozone. Those are the 2 resonance structures possible for ozone. And that's the end of our little practice video here for part 3.